Hello, my name is Carl Calamari, and today we're going to be solving the problem 2007 Calculus BC number 6. The problem goes as follows. Let f be the function defined by f of x equals e to the power of negative x to the power of 2. A, write the first four terms in the general term of the Taylor series for f about x equals 0. So we're given the function, and we have to convert it to a series. And even though it asks for the first four terms first and then the general term, we should start with the general term first and then solve back and plug in values for the first four terms. So they asked for a Taylor series for f about x equals 0. Now x equals 0 was what made solving for the Taylor series difficult, but we have to remember that a Taylor series that goes about x equals 0 is the same as the Maclaurin series. So what this tells us is that we can basically ignore this and write Maclaurin series. Actually, I don't know how to spell it. I think it's like this, Laurin series. And there are certain rules that are really helpful for converting functions into series. So it fundamentally should start off like this, and then we can remember the rule for e to the power of something, which is n squared of negative n squared to the power of n. Let me confirm that's correct. Yeah. So this will be our general term. So we got one part of it done. Now the first four terms, all I have to do is plug in 0, 1, 2, and 3. So what we'll get is when we plug in 0, we get 1 plus, when we plug in 1, we get negative over 1. When we plug in 2, we get 2 over, I believe, yeah, that comes like that. Oh, yeah. What we can do here is make it easier for us to read. This is the same as what many of you will want to do. This is a good habit to form, is to take out that negative so it becomes an alternating sequence series, and it makes it a lot easier to see. So this will be positive, this should be negative, so this negative can be brought down here as positive, and then again it's a negative, which is if we look at this, it should be 6 over 3 factorial, which is also 6. Now, we have to write the general term as well, so this is plus, dot, 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 plus. We don't have to write the series, the sigma notation for this one, we just simply write as what we got, plus, dot, dot, dot. And just to quickly review over what we've done, you have to, these four terms here will get you 2 out of 3 points. You will get 1 point if you get at least 2 of these terms, and you will get 1 point for the general term. So in total there are 3 points, and the key takeaways are to make sure that you recognize when the Maclaurin series is present, and remember the formulas, and not making mistakes, and taking out the negative 1 will be helpful for avoiding mistakes with the signs. Welcome back. Now we're going to get started with solving problem B. Now part A was actually the difficult part because we got the general term, which is going to be the basis for everything else that we build on with the remaining 3 parts of this problem. So part B states, you can answer from part A to find limit as x goes to 0 of this value. So if we recall correctly, f of x equals that, but we solve for the general term, which is this. And now this is very helpful because when we see terms written out like this by themselves, not contained within the series, we can pretty much ascertain we'll want to write this out in its extended polynomial form, which will look like basically what we did before, 1 minus x squared over 1 plus 4 over 2 minus x over 6, which is 3 factorial, plus dot, 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 plus, the general term equals that. So when we see something like this, we know that this extended polynomial will fit into here, so it will look like 1 minus that over 4. And what happens now is we can do some basic manipulating of common terms, and what we'll have here is this and this cancel out, and this cancel out. Because this is a negative, all of these signs will change. This becomes a positive. Everything of that is, did I wrote this wrong. It should look like that. X to the power 4, not just 4 by itself. So that goes here as well. And what we have remaining is over 2 minus x over 6. Actually, this is a plus, and this is a minus, plus dot, dot, dot. Now, there's a very common mistake that people make is that they forget to apply this negative sign to all of these, not just, you'll do the hard part and forget that you have to apply the negative to all of that. So all of this over -4, and don't forget that the entire thing is limit of n of x, sorry, not n, goes towards a 0 of all of this. And dot 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 dot, what we have here, I don't have enough space, so I'll just simply erase it, is we divide everything by x to the power 4, we get negative 1/2 plus x over 2 over 6 minus dot dot dot. Everything beyond this part we can disregard because as x goes to 0, all these will simply turn to 0. And we get the only constant left, which is negative 1 over 2. And this is our answer. I believe we get 1 point. We only get 1 or 1 point for coming up with the final answer. And now we're on to part C of this problem. Now I'll read it out for you. Write the first 4 non-zero terms of the Taylor series for integral 0 to x of our function dt about x equals 0. Use the first 2 terms of your answer to estimate the integral, but to negative to 1/2. So this problem seems like a lot right off the bat. It looks like we'll have to integrate something, which is going to take a lot of time if we do decide to do that. But a principle that all of us should remember by now is when a series, a Taylor series, goes is about some value, which in this case is 0. If we start our integral from that value, which is 0, all we have to do is simply integrate the entire thing and not worry about the constants that are left over. So, for example, if we have our original extended form of the series, it'll look like it's like this. You have to do minus, and then this is a 1, so 1 plus x to the 4 over 2 minus x to the 6 over 6 plus dot 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 dot. We're trying to find that. These should all be t's. You get the point though. It's going to look like this. Because it starts off at 0, all we have to do is integrate all of these. So we get from x to 0, x minus x over 3 over 3 plus x over 5 over 10 minus x over 7 over 42. And there we go. These are our 4 terms. Let me check if I'm correct. I didn't make any errors. Yeah, these should be our 4 terms. And what happens is dot 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 dot. It just goes on like that. This is this. So 4 terms down. Let's go. And the problem asks you the first 2 terms of your answer. So the first 2 terms are these: x minus x over 3 over 3. Maybe right, that's a little bit messy. X minus x over 3 over 3 to estimate negative 1/2. Now all we have to do is plug in. Did I say negative? I meant positive 1. All we have to do is plug in 1/2 because it will look like this. 0, obviously that becomes 0, so there's a minus 0 here. And if you plug in 1/2, you get 1/2 minus 1/8 over, so 1 over 24. And we do some mental math, that's 12 over 24 minus 1 over 24 equals 11 over 24 minus 0. So that 0 goes away, and that is indeed our answer. So in a lot of ways, this is similar to part A because we get 1 term for having at least 2 terms of our 4 terms. We get a second point for having all 4 terms, and we get 1 point for the correct answer for a total of 4 points. And we are finally at the final part of this calculus problem. Explain why the estimate found in part C differs from the actual value of our integral by less than 1 over 200. So right off the bat, we know that when it asks for less than something, or why your estimate differs, these are keywords that tells us that we are solving an error problem. Now, in BC, there are 3 errors, but only 2 of them really pertain to series. One of them being the Lagrange error, and the second of which being just the alternating error test, or just alternating errors, what it's called. So all we have to do now is before we start any of them, we should remind ourselves what the terms look like. So we proved in part C that the first 4 terms of this is x minus x over 3 over 3 plus x over 5 over 10 minus x over 7 over 42 plus dot 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 dot. And we used the first 2 terms in part C to, when we plugged in 1/2, we got 11 over 24. That was our answer to part C. And now we have to prove why our estimation differs from the actual value by less than 1 over 200. Now the actual value obviously is this entire infinite sequence added together. Now what we should be able to notice right away is that because our value has an alternating, negative 1 to the power of n, all of these are going to be alternating. So that means that the alternating error is perfect for this problem. Lagrange, I'm not sure if it'll work. If it does, it will massively overcomplicate things. So what we do is we take, see this is the value that we ended at. We take this value right here, and we take it out. We have x over 5 over 10. Now, what we have to do here is plug in a 1/2 into x, we get 1 over 32 over 1 over 10, which is 1 over 1 over 320. Now 1 over 320 is obviously smaller than 1 over 200. Now part of the problem will ask you for your justification or your explanation. Just writing it like this will get you your point. And it's crucial to state that you use alternating error. And not only did you use alternating error, you should remember to write out your did I do that correctly? Yeah, you should write out your Taylor series that clearly shows that's an alternating. And we did not actually solve for the Taylor series of this, but it shouldn't be that hard to. I'll just write it here for you guys. The contents of this series are not really that important. All that is crucial to show the grader is that we have this, which proves that's an alternating error. And thus, when we solve for these two, the sum of this, I believe the error of that will be at most this term. And because this term is 1 over 320, and the error is at most that, the error can be clearly defined as being less than 1 over 200. So that is our proof. And which one series includes an absolute value of 0. Using the third term as an error bound is significant in this problem. That gives us 1 out of 2 points. And our explanation also gives us 1 out of 2 points for a total of 2 points. Now that is the end of the problem. If you want more problems like these to practice by yourself, I found 2012, problem 6, and 2008, problem 3 are similar problems. Problem 3 from 2008 has more error-oriented stuff, and this is a little bit hard. Problem 6 has more problems pertaining to the solving for the general term of series and such. And these are a mixture of both topics, which will help you master these type of problems in Calculus BC.